So hello, everyone. Today I'm going to give you a talk to present an unsupervised algorithm for disaggregating low sampling rate electricity consumption of the households. Probably you have seen already something yesterday in the poster, so today I'm going to give you a bit of more broader overview of how does it work. There is no clicker, right? Okay, perfect. Perfect. But before I go to the algorithm itself, I want to say a couple of words of where I'm coming from. So I work in the PV lab in Neuchâtel in Switzerland. So it's a lab whose core expertise in photovoltaics. So basically what we're doing there is that we work on the development of different solar cell technologies, such as heterojunction, perovskites. But as well, apart from this, we work as well on the system side. So we are interested in how do we integrate PV in the grid? How do we work with the building energy management? And what we can do with the storage technology. So this is a little overview of the activities that are conducted in the lab. So moving on to the algorithm. So we call it a device usage estimation algorithm. This is an unsupervised algorithm working with the residential setting. However, already here, I want to emphasize that the point of this algorithm is not to go to the device disaggregation, so we're not trying to track every single appliance, but we are rather working with group of appliances and we link them with the activities, which you will see now. So first, to give you three main highlights about the algorithm. So it's unsupervised, as I already said. There is no training required, therefore it removes the need of collecting data. Second, this algorithm works with the low sampling rate. So typically, we are working with the smart meter data, which is at 15-minute resolution. And the third main point, that algorithm performs an efficient computing. You will see it later in the section when we compare it with some other algorithms. But the main point here is that with the growth of the amount of data, our algorithm scales linearly, opposing to the, let's say, exponential growth that we have seen usually in some other algorithms. So how does it work? So our device usage estimation algorithm is based on the Markov model. And the main idea here is that we are not trying to infer categories of appliances by directly looking at them, but rather this is a following sequence after we're trying to infer the activity chains of the people that are living in the house. So what we are using as an input to the algorithm, so basically here we concentrate our attention on three main points. So first, of course, we use the active power load curve. So this is the smart meter data we have talked about. Second, we're looking at the basically calendar data. So what is the type of the day? Are we talking here about the weekday? Is it a weekend? What kind of day is that? Then we look at the household characteristics. Saying household characteristics, it's mainly to emphasize here we're looking at characteristics of the people who live inside the household. So we are interested in their employment state and the age group and subcategories you can see on the slide. So this is basically the main inputs of the algorithm. The algorithm is based on the time of use survey. So actually from this survey, we're getting out the probabilities of some particular activities that can happen inside the house. And what do we get as an output of the algorithm is basically an activity chain that is constructed for each person living in the house. After we have activity chains made up for each of the person, we run the optimization problem to see, okay, what is now the error between the constructed load curve that we took out after making these activity chains and the one that we put at the input to the algorithm. So we have main assumptions to have a look here. So basically, as we have seen previously, one of the inputs to the algorithm is, let's say, the age group of the people. So we want to emphasize here that children below 10 years, they are not considered to have their own energy needs. So their energy needs are rather coupled with the energy needs of the adults. The teenagers, they have a random activity chain. So we're not trying to optimize their activity chain, but rather we're using a random process to generate it. That's a different question when it comes to adults. So when we talk about adults, we use an optimized activity chain. So here there is a full optimization process running in order to understand what is the most real active chain we can generate for an adult. You can see here on the slide that after we have inputted our data into the algorithm, we run the pre-treatment process. And when we talk about the pre-treatment, first we need to filter out the standby from our load curve. Rather, after we try to filter out the fridge. So basically, we try to see the repetitive pattern during the night consumption. These are two elements we are removing from the load curve. And further, we are trying to detect the peaks. Why do we need the peaks? Because this can actually explicitly tell us about the occupancy state in the house. And we consider that there is no partial presence or absence that can be detected. Rather, that if we see a peak and it's a presence, we know that in this case, all the inhabitants of the house are going to be inside. So we're going to generate an activity chain for all of them at the same time. So I told that we are looking at the categories. So what kind of categories we are working with? So basically, we are interested in 8 main categories. So here we're talking about cooking, ICT, housekeeping, entertainment, light, fridge, heating, and standby. But because categories is something that comes after inferring the activities, they are the main activities that we're considering in our work. You can see on the right, there is a list of activities we're working with, and there are as well activities that are considered, let's say, the ones that are not using any kind of appliances, such as sleeping and outdoor. So these are activities that are not actively related to inferring appliance categories. And here you can see the related connection. So what is the workflow of the algorithm? So first, as I already said, we are doing the pre-treatment to infer 2 main categories, standby and fridge. Further, we're working with the optimized activity chain. As I already said, optimization is happening only for an adult. So for teenager, there is no this step happening. It's a random generation. So when we talk about optimizing activity chain, we're basically selecting activity based on the probabilities we have inferred from the time of use survey. And the next step is to recognize the load profile. So here on the left, you can see the main chain of activities that we do in order to recognize the category here. So we start with heating as the highest consuming category, and after we work step by step sequentially to infer other categories. One thing to note here is that for categories such as light and entertainment, it was considered that basically these activities related to these categories that can happen at any time and that can run in parallel to some other activities. So for example, if you're doing your housekeeping, you might have a TV turned on as well as the light. So these activities are considered in this way. When we talk about light, another important thing to note is that for each person that is living in the house, the light category that is associated with them is multiplied by some factor, which is, I think, around 0.25 that we used here, in order to not multiply the usage of light into some unnecessary boundaries, but rather keep it realistic. So this is the main workflow we have talked about. But of course, when you do an algorithm, you have to understand where does it stand in terms of comparison with other algorithms that already have been implemented in the literature. So we decided to do the following comparison setting. So we looked at these main 4 algorithms, such as combinatorial optimization, FHMM, graph signal processing, and discriminative disaggregation via sparse coding. So these are the 4 algorithms we have decided to compare our with. We did it on 3 main data sets. So here it's ecosmartenergy.com and UKDale. And the thing to note here is that they are located in the sequence because the amount of data we used for the training and testing here in EcoSmart Energy and UKDale is increasing. So the highest the longest data set was the UKDale here. And because we are not disaggregating particular appliances, but rather categories, we needed a different metric in order to assess, well, the feasibility of this disaggregation. So we worked with error on the energy share and the normalized mean square error. So moving further to the results of the comparison, here you can see the graph on the uncertainty on the energy share. So basically, this graph is the one graph that is telling us across all the data sets what kind of performance we are getting compared to other algorithms. There are several main things to note here is that you can see first that obviously the performance is not consistent across all the categories. And this is, this is quite understandable. The average uncertainty share on the energy is around 20%, though we see that, for example, on the ICT category here, the device usage estimation algorithm is above this boundary, so probably there is still room for improvement. However, we can see that mainly there are 2 points why this might happen. First, compared to all other algorithms, ours is unsupervised, so we're not using any kind of training phase. So due to this, the performance might be a bit worse sometimes. The other thing is that As I already said, it's a survey-based algorithm, so for each data set, it was assuming that all the same categories are existing. However, that we know that for some of the data sets, for example, there was no housekeeping category, or there was no, for example, some other category. Therefore, there is this imposed assumption that all categories are present, that sometimes it can degrade a bit the performance. When you look at the normalized mean square error here, so this is as well the comparison between different algorithms. We have identified that basically more or less acceptable level is around 2 here. However, you can see it's really highly dataset dependent. For example, you can see that for ICT, for the ECHO dataset, our algorithm performed even better than the DSC. However, there is a controversial situation as well here for heating. So though we defined some acceptable deviation for all the algorithms, however, it's really, let's say, case-on-the-case basis how to interpret this performance. To continue, let's say to state the main conclusions. So what kind of algorithm we did? Well, it's an unsupervised algorithm based on 15-minute data. It's, as I already said, we found out that the algorithm actually scales linearly with the amount of data. So this you can see on the graph here. There is the GSP that we did not test on the UKLD because the algorithm was, the data set was a bit too long to test it. But however, here in yellow, we can see the device usage estimation algorithm, which is in its computation capabilities is close to the easiness that we have seen in the CO algorithm. And as already mentioned, the potential use of the algorithm, we were not interested to disaggregate to appliance level. What rather we want to use this algorithm for is to try to think what kind of new flexibility, for example, services we can provide to the grid. So this information is rather can be used by the utilities in order to formulate some new services at the low cost that they can provide to their customers. And the last mention that I want to make here, that this is a publication that was submitted, so soon you will be able to see it in the journal and probably get more details out of this. And last thing, I want to thank you all for your attention. As well, I want to thank our financial sponsors. It's the Swiss Federal Office of Energy, the European Commission H2020 program, and the SCCR Purist project in Sweden. If you have any kind of questions, you can contact us on the following emails, and we'll be happy to reply them. Thank you so much.